hello.
I'll start out just on Synaptic. I'm co-founder and chief data scientist. I'd say about 10 years ago, my partner and I started the company and we did AI machine learning consulting projects. And so people would have us come in, we would solve a problem for them, and then we would go away. And over the years, as the company's grown, we've become a bit more integrated into the entire life cycle. So these days, we do a lot of data strategy work, helping companies try and understand how to position themselves to be ready to make use of the data that they've got. We do a lot of data engineering these days as we've gotten into larger projects. There's more data floating around, and you have to be able to do that efficiently. And then also, a lot of the things that we're building tend to be user or customer facing. And so we've taken on work in product and user experience, for example. So the way we kind of characterize the company is that we build intelligent products. So just a little bit on the company so you know where we're coming from. Before I get to the outline, I just want to say a few words to kind of motivate what I'm doing today. So I have lots of conversations with people from lots of different industries about us potentially helping them solve problems. And every conversation at some point comes back to three things. You might want to think for a second, what are the three things that every client wants to know about? You can probably guess one of them based on the topic for today. But they want to know, how much is it going to cost? How long is it going to take? And how much data do we need? Now, I put the data at the bottom of the triangle on purpose because it's sort of the foundation from which everything flows. On some level, the first two questions are easier, right? So you kind of get a handle on, this is a project of this size, it's probably going to take this long, but the data influences it. So, as you'll see in a minute, there's a very important lesson that's been learned in AI and machine learning is that if your data is not in good shape, or if you don't have a lot of data, you have to work a little bit harder. Now, that doesn't mean that you can't do interesting things with the data. Otherwise, we wouldn't be having this conversation today. But data is foundational for sort of everything that you want to do. So, what's the outline? I'm going to start out just talking about factors that influence what your data needs are. What are the circumstances that put you in a situation where you would need more data or less data? And then we're going to look at three broad categories. So, sometimes you just don't have a lot of data. We'll talk about when that can happen. What are you going to do in that case? Sometimes you've got a lot of data, but you don't have many labels. And I'll talk about what that means in just a minute. But think about a label as the thing that you want to be able to predict. Is that machine going to break or not, for example? So I might have lots of raw data, but I haven't had experts apply labels to much of it. And then sometimes you literally have no data for trying to train up a machine learning algorithm. And interestingly enough, you could actually deal with that case these days. There's no free lunch, and you'll see what I mean in a minute. But you can roll into a situation where you want to solve a problem, you don't have any data, you can kind of talk to the machine a little bit nicely, and it'll go, okay, yeah, I can help solve your problem for you. And then we'll have some concluding thoughts. So, first thing I want to do is talk about what influences how much data you need. To do that, though, I'm going to stipulate that we're going to talk about a certain kind of AI, which is a certain kind of learning, which is supervised learning. And in supervised machine learning, you've got a data set, which we're going to call a training set, which has things and they're labeled by their type. So in that little picture there, you've got email messages, those are the things. And then, clearly the machine is going to look at, for example, the content of the email messages, right? But the email message is the thing. And then the type is it important or not, right? But very broad kind of general setting. It could be that you've got an acoustic recording and you want to know, is that machine going to break soon, right? Like, is it starting to make funny noises that we might be able to detect? You could look at even more complicated things like sort of sequences of bank transactions. You've got individuals and financial institutions and movement of money, building out this sort of web of interactions. And you want to know, is there fraud? Or you can have very, very sort of dense information in video, for example, surveillance video, and you want to know if there's a crime occurring. So we're going to talk about supervised learning. In this case, as I said, you typically think about having training data. And on the left, we've got, imagine there's email messages and there's spam, and then there's like, requests that you need to pay attention to. That training data is handed to a machine learning algorithm that produces what we call a model. And what that model does is it takes some data instance that you haven't seen before, like a new email message, and tells you what it is. Is it spam or is it something that you should pay attention to? You can think about supervised machine learning as producing this function f that is the model. So the model then is going to take an x which is an email and produce a label, right? So the function is what's learned. And clearly, how hard it is to learn that thing is going to influence how much data you have. You give it an X, which is an email, an acoustic recording, a video, and then it says, like, here's what that thing is. The machine's going to break or it's not. Given that background, why do you need more or less data? So I'm going to think about two ways of looking at it. One is if I have a lot of prior knowledge about the problem, then I might need less data. And if I don't have much knowledge about the problem I'm solving, then I might need more data. So what does that mean, right? So you and I learn things all the time. We never learn from scratch. If you've played tennis before, then which is on the left, then learning to play pickleball is probably going to be easier. So in this case, prior knowledge is I have experience with a similar problem, and we're actually going to see that being put to use in the machine learning context. So if you've played tennis and you know how to do that, it's going to be easier to learn to play pickleball. On the other hand, if you've always been a couch potato, you've never played any sports whatsoever, and you just roll onto a pickleball court, you're going to have a harder time learning it because you've got to learn all kinds of other stuff. You got to learn how to hold the racket, how to swing the racket, how to follow the ball, that kind of thing, right? We'll ground that out in machine learning in just a minute. Another thing that influences how much data you need is how complicated is the thing that I'm trying to learn. So if it's simple, like tic-tac-toe, then I might need less data, right? Tic-tac-toe, there aren't that many states that the board can be in. You can sort of look at lots of games and pretty quickly kind of figure out how to play tic-tac-toe. And, in fact, I've assigned that in undergraduate AI classes. However, if you're playing something more complicated like the game of Go, which is much harder, right? So IBM developed Deep Blue, which learned to play chess, and it wasn't until AlphaGo came out a number of years ago that a machine learning system was able to solve playing Go. And it turns out it needed lots and lots and lots of data because it's a much more complicated problem. So there's this notion of, can I sort of leverage things that I know about the problem to make it easier? But even so, how hard is the underlying thing that I'm trying to learn? There's a great paper. This is old. I can't remember when it came out. I'm going to say it was in the early 2000s called The Unreasonable Effectiveness of Data. And basically what that paper showed was, this was a sort of what I would call old school machine learning algorithms, but I think the basic tenet holds up, which is if you don't have much data, it makes a big difference what algorithm you use to try and learn from it. And so what they showed was with small data sets, different algorithms would perform differently, which is perhaps not surprising. But then as you scale up the amount of data that you have, as you get more and more data, the differences disappear among the algorithms. The idea being that a lot of data can make up for faults in underlying algorithms or simple differences in algorithms. And so the way I think about it is the more data you have, the less clever you need to be, right? You can sort of do the simple thing often when it comes to learning. And if you've got enough data, it'll just be fine. It's harder when you don't have enough data. Okay, I'm almost done with the intuition. I just want to sort of drive it home with a really simple example here. So we're going to learn a function. Remember, I said they've got this y is equal to f of x. So this is, just like you were in junior high school, but we've got x and we've got y. And we want to say, oh, well, what's the function that if I give it the value of 2, it's going to give me 3. And if I give it 4, it's going to give me 4. So I'm asking you, is 2 points enough data to learn that particular function? The correct answer is you have no idea because you don't know anything about the function. I haven't told you a thing. Now, if I tell you that it's a line, your good old-fashioned y is equal to mx plus b, or it's, the slope plus the y-intercept, then you go, of course that's enough data, right? Because 2 points make a line. If that's a case where you knew something about the form of the thing you're trying to learn, and you go, oh, well, 2 points, that's all I need. Now, what if I tell you that it's a parabola, right? It's a more complicated function. It's got a square term in there. Well, in that case, 2 points isn't enough. Here is one parabola that goes through those 2 points. Here's another one. That's not enough data to do a good job of learning that function. And then you're like, okay, what if other circumstances? What if you know it's a line and you know the slope of the line? Then you only need 1 point, right? You're like, oh, 1 point suffices because I know more stuff about the thing I'm trying to learn. If, on the other hand, it's a line but the observations are noisy, you're going to need more data, right? So we've got 2 points. Who knows? Maybe it's like the data is sort of aligned like that, or the data is aligned like that, right? If there's noise, we know less about what's going on. We need more data. And if you have no idea what the form of the function is, which is typically what happens in machine learning circumstances, you're going to need more data. So again, this is my sort of I'm trying to drive home about the more you know about sort of the underlying form of the thing, the less data you're going to need. Okay, let's jump into the three cases. So the first case is there's just not much data. And we see this a lot. So early stage companies. So for example, you're selling some product to customers and you want to predict customer buying patterns, right? You're early stage, you got a few customers, you want to do the best you can, trying to, sort of leverage that data, but you're going to have to grow for a while until you have, what you might consider enough data. Also, physical data collection can be hard. So if you're flying drones over pipelines and you're looking for defects in the pipelines, right, that's a very slow process and it's harder to collect data. So what do you do if there's just not much data? And what I'm going to do is I'll talk through some strategies that we've used at Synaptic and they're very common. Some of them are very applied and have been very successful. Others are just a little bit more theoretical. Now, this slide's got a lot going on it, but I want to explain it. I just want you to take away the intuition. So there's this thing called transfer learning. And think about this top stuff being tennis and the bottom stuff being pickleball. Transfer learning says, I've learned to solve some task, and now you're going to have me solve a task that's, kind of like related, similar. And what I want you to do is leverage what you learned from the first thing that you did. Okay. So let me just take a couple of minutes to walk through this thing because I just want to make sure. I mean, some people look at this and go, yep, totally know what's going on. Others are like, I have no idea what's going on here. I'd like everybody just to at least have the intuition. What you're looking at here is just a set of images. So what we're going to do is we're going to build a machine learning, a supervised learning classifier, which is a neural network that takes an image and says, does it have a dog or a cat or a spoon or any of literally 1,000 categories, right? Now, modern machine learning systems, typically you can think about them as having two components. One is I got to take an image and I'm going to learn a representation of that image that is just a vector of numbers. So, what that means is every image that gets handed to me, I'm going to turn it into a list of 1,000 numbers, for example, 1,000 real numbers. The idea being that you would like it to be the case that two pictures of cats are going to have similar numbers and two pictures of dogs are going to have similar numbers or vectors of numbers, but the cat and the dog are going to look a little bit different, right? So we call the first part representation learning, which is just how can I take a picture and turn it into a list of numbers so that that list of numbers conveys something very useful about the content of those numbers, right? So that first part says, I'm going to learn to take a picture, turn it into a list of numbers. The second part is, in some sense, the classifier, the thing that actually learns to work with those vectors, right? So this part we train up as well. It turns out we train the entire thing end to end, but this part learns to encode an image. And then this part says, okay, you're going to give me a vector of numbers. I'm going to learn to figure out whether that vector of numbers has a cat or a dog or a spoon in it. So this is, I've been playing tennis and I've learned to play tennis quite well. Now, what happens is in transfer learning, what you do is you say, I'm going to move to a completely different domain. So maybe I've got medical images. And I want to reuse what I learned when I was classifying cats and dogs and spoons. The idea in modern machine learning is that I can probably still use the representation, right? So you've learned a way to turn images into vectors of numbers. Those vectors of numbers, similarity between those vectors of numbers convey image similarity or semantic similarity. So what I'll do is I'll just chop this part off, right? I'll keep this part, and then I'll just train a new classifier on it. So I'm going to borrow what I learned from the first domain to use it to encode pictures, but I need to learn to tell whether I've got benign or malignant. That's misspelled, but you get the idea, right? So is it benign or malignant? The idea here is transfer learning says I've learned in one domain, and what I'm going to do is I'm going to borrow that thing, which might have been trained up on lots and lots of data. ImageNet's a massive data set. And it turns out that that's very common. It is very rare to actually train something completely from scratch. Training this part takes a ton of data. Training the classifier takes way less data. So what we do is we say somebody has gone to all the effort. They had a massive data set. They've trained up that whole representation part of it. I'm going to borrow that, and then I'm just going to use the little bit of data I have here to train a classifier for the thing that I care about. That's transfer learning. Now, much easier concept is just open source data. It might be that you don't have a lot of data, but there might be data sets similar to the thing that you're working with. So we've made good use of, for example, Google has a data set search facility. You can go to Google and Google data set search, and you'll land on their webpage. There's also the website Kaggle, which is used for lots of purposes. Lots of data sets are hosted there. There are these competitions that people engage in to try and solve machine learning problems on the data sets. But the idea is that often you can find an open source data set that is close enough to the thing that you're doing that actually augmenting your data with that data can get you further. So you can train on a blend of the open source data that you found in your data, kind of get the model going and working reasonably well, and then start like sort of homing in on just the data that you've got. So transfer learning basically says, hey, you've got a piece of a model that you trained up on a large data set. I'm going to grab a piece of it and fine tune it on my data. This says, hey, I'm going to go grab some additional data from the web. And then finally, if you don't have a lot of data, you can do data augmentation. So data augmentation is sort of a core practice in machine learning these days. And there's lots of ways of thinking about it, right? So you have a sentence that says, I have no time. Now, maybe that sentence is labeled as being, I don't know, optimistic or pessimistic, whatever, right? So there's some label associated with it. And you want more pessimistic and optimistic statements. You could do this very simple trick, which is to use Google to translate it to some other language like French and then translate it back. The idea is that round tripping it is going to preserve the semantics, the meaning, the sentiment, right, whatever, but you're probably going to wind up with slightly different wording. So in text space, there are lots of ways of kind of taking sentences, like jiggling them a little bit in various ways. This is a particularly clever way of doing it. And then winding up with a sentence that means the same thing, it's phrased differently. But whatever the label was for the original sentence, you're going to keep the label for the augmented sentence. A little more common to do it in the visual domain, and this is just part of everyday practice when you're learning on images, is I've got a cat image, but what I can do is I can just modify that image trivially, right? I can flip the cat on its head, I can rotate it, I can add some blur to it, I can change the exposure, the contrast, I can convert it to grayscale. All those things are still cats, right? But now I took this one image and I created six more images from it. There are many different augmentations that you can apply. So what this allows you to do is to take a single labeled image and then generate plausible variants of that thing that you can add to your data set. So now, you can multiply the amount of data you have by a factor of 10, for example. All right, so that's data augmentation, which says I don't have a lot of labeled instances, but I'm basically going to create more instances by this method of augmentation. And there are lots, very well studied, lots and lots of different ways of tackling that problem. Web scraping is one that we've used a lot. We actually did a project with a company that was looking at doing automatic license plate recognition. And part of that was to try and identify the state that it was in. And 50 states, there's a lot of variation. They didn't have a ton of data from all the states. Actually, they were deployed in certain states and they had lots of data in those states, but not in others. And so turns out we just sort of automated going to Google and saying license plate Michigan, license plate Maryland, license plate California. Now, you're not guaranteed that the things that come back are license plates from those states, but very high probability. Web scraping of that form of just saying, I want to Google for the thing that I'm looking for in image search, and I'm going to take those images and assume that they belong to the category I'm looking for. We also did a human activity recognition project. It was human activities for young children, and we did exactly the same thing, right? Turns out people are very fond of posting videos of their children doing things. In this case, it was video. And so we would, Google, child crawling or whatever, and we got tons of video that way. So web scraping is a viable approach. So that was the first case where I just don't have much data, right? I'm supervised learning. I've got things, I've got labels, but I don't have many of them. The second case, which is actually pretty common, is I've got lots of data, but few labels. So, think about this. You can, if you want to, you could go download all of Reddit. So I've got all this text, but maybe I want somebody to label it for me. Again, maybe I'm doing sentiment analysis or something like that. So I've got a ton of data. 99% of it is unlabeled. Some of it is labeled. How do I leverage that? Could be there's a high cost resource. So I've worked with doctors and they're super expensive, as you're aware, and getting time for a radiologist, for example, to come in and look at some images and go like tumor, not tumor, very expensive. So what you want to do is to not overuse that human resource. Now, that's the second case that we're going to talk about. So there are a few things you can do here. One very common one is a thing called active learning. Remember the sort of process that we go through in machine learning that we talked about. We have labeled data. We've got things and their labels, right? So these like little time series and little labels here. That label data then gets handed to a machine learning algorithm that trains a model. That model can make predictions, and it's making predictions on unlabeled data. Now, what active learning does, in essence, is it says, hey, I made some predictions on that unlabeled data. I'm going to have a way of sort of looking at that unlabeled data and the predictions I made and picking specific ones that I would like to be annotated by a human. Instead of saying, hey, human, I just need you to label lots more data, you will pick the instances to label, or you would, pick the things to label that you think are going to help you learn the best. And actually, I think we as human learners do that a whole lot, right? We don't randomly sample problems from a textbook as we're studying. We tend to go, oh, like, I don't know, that's kind of hard. I don't really understand what's going on there. Let me go to my human teacher and ask them about that. And so often what active learning systems do, you can think of it as kind of choosing the hard examples. Now, here's a diagram to try and drive that home. This is imagine that we've got our things are points in two dimensions, right? This could be mushrooms, and this axis is their height, and this axis is their width, right? So you can get skinny and wide mushrooms, you can get short and tall mushrooms, and plus means it's poisonous and negative means it's edible or whatever. So this says, hey, there's a mushroom that has that height or that width and it's poisonous, for example. The active learning situation looks like this, right? So we've got a bunch of poisonous mushrooms, we've got a bunch of edible mushrooms, and then we've got these other dots around here, which are unlabeled instances. And an active learner typically says, I want labels that are going to be most informative about where I should draw the line between the two. And those tend to be the ones that are closest to the line. Many active learning systems you can think about is saying, well, I don't know, like if that line moves a little bit, right, it'll control whether those dots are labeled as poisonous or edible. Let me ask the human to label those instances, and that's going to help me figure out where I should put that line that separates those categories, right? So this is again, I've got a bunch of instances. Some of them are labeled. I'll learn a model and I'll ask the model, hey, what instances that are unlabeled do you think would be most helpful to you if you label them? And I'll just go ask the human to label those so that radiologist isn't hammered all the time. There's another sort of very interesting approach, which is called self-training. And I'll walk through this. So in self-training, what you do is exactly the same setup, right? So I've got some labeled instances, some unlabeled instances. The ones that have labels are the ones that I can learn from. And so you go, okay, it's exactly like active learning. I'm going to take the ones that have labels. I'm going to learn a model. Now I can make predictions about things. The difference in self-training is that what I do is I go, oh, you know what? I labeled these instances that were unlabeled previously, right? I used my model to tell me, I think that mushroom's poisonous, or I think that's a tumor, for example, in the image. And what I do is I say, well, the ones that I'm very certain about, I'm just going to pretend that that's the correct label. So now what I do is I take the model, it assigns labels to the instances that it's very certain about, adds those back into the label data set, and then trains the model and iterates. The difference is if you kind of look at this picture again and imagine where are the ones that you're very certain about. If the ones that I'm kind of unclear about are the ones that sit near the boundary, then the ones that I'm certain about are kind of far away from the boundary. What this pseudo labeling or self training is doing is it just says, well, I don't know, I feel like that thing that was unlabeled is one that is in a region that I really understand well. I'm just going to assign the label I think is correct, pretend that it's true, and iterate. And so you can see that through time, you can sort of build out the size of your labeled data set as the regions of certainty get to be larger and larger. Now, again, remember we're in a setting where we've got lots and lots of things without their labels and a few with the labels. Remember what transfer learning did, right? So remember transfer learning was, oh, somebody came along with a giant, fully labeled data set, and they built this model that uses images as input. And as part of that process, they learned a good representation for images, right? Remember, the idea of a representation is it's just a mapping from an input thing, like an image, a blob of text, a social network, and all those things, in all cases, we're just trying to turn them into a vector of 1,000 numbers, for example, right? And then what we do is we say, okay, now that we've got that nice mapping, that nice what we call the encoding, We'll say, now we're going to use that, and then we're going to like take a few labeled instances and train up a classifier using the labeled instances, because all we have to learn is like this little thing here, right? We don't have to learn this thing, which tends to be much more complicated and require more data. The question is, what if we've got this situation where we have lots of unlabeled data, but we don't have a good pre-trained model in our domain? And actually, it's kind of hard to go from ImageNet to medical imagery, right? Because they're very different. So, I'm collaborating with some people looking at ultrasound images right now. And every time I've ever looked at an ultrasound of any kind, it just looks like complete noise to me. So it's hard to imagine that pictures of cats and dogs are going to translate well to ultrasound. So what do you do? Well, here's an exercise. I show you that. And I'm going to ask you to draw the rest of the picture, right? That's a window into a larger picture. Can you draw the rest of the picture? Now, you look at that immediately and go, okay, that's a giraffe. And furthermore, that's the neck of the giraffe. And it looks like they're sort of in a, setting with trees, for example. Now, how were you able to do that? It's because you know a tremendous amount. You have a lot of background knowledge. So you go like, boom, okay. You might not have drawn that. And if it was me, I would have drawn the giraffe poorly. But everybody, when you see this thing, you go, okay, I can fill in the rest of it. Now, the fact that you can fill in the rest of it means that you have a tremendous amount of knowledge about the underlying domain. In what's called self-supervised learning, we do this kind of thing. And so what we're going to do is we're going to learn to build a representation of your data without needing any labels. So if I've got pictures of things, or if I have financial transactions, or if I have text, and this is exactly what large language models are doing, what I'm going to do is I'm going to take your data and I'm going to hide part of it. So I'm going to hide that little square of that image. Or I will take your network of financial transactions and I will hide a couple of edges. Like, right, I'll go, I'm not going to show you that that particular money transfer took place. Or in text, I'm going to give you a sentence and I'm going to block out one of the words. And what your goal is as a machine learning system is to learn to fill in the thing that I've hidden. And clearly, I don't need labels for that, right? I just need raw images, I need raw text, I need raw financial transaction graphs. And what I can do is I can hide it and I can just train up a system that goes, given what I see around it, I think I can fill that in. And so you can train a system to do that. And what that does is it learns the representation for you. So now, if you remember what was going on before with transfer learning, we would learn to solve a complete end-to-end problem in one domain and we would borrow the representation, right? In this case, what we do is we use your data on both sides of it. So we have data here, and we have this thing's called a pretext task, which is basically just, can you fill in stuff I've blocked out, right? I'm going to mask things. There are tons of ways of structuring these pretext tasks. The most common one is this idea of masking and filling in. So I'm just going to take all this unlabeled data that I've got. It's self-supervised because I don't need any labels. I'm just blocking things out. And it turns out that if I do that, I can learn a good representation, which is key, right? That's one of the lessons of kind of machine learning over the past 15 years, is the ability to learn these representations is incredibly useful. And then I switch over and go, okay, I'm going to use my little bit of labeled data. So I've used lots of unlabeled data to learn a good representation. I'm going to borrow the representation. And then I'm just going to do the same trick I've been doing all along, which is, oh, got a little bit of data. I could put a tiny little classifier here that's easy to train up, doesn't require much data, and boom, I'm good to go, right? I should say, to kind of connect this back to some of the stuff that I said at the very beginning, this is essentially, I've got a lot of prior knowledge. So just like you had a tremendous amount of prior knowledge about the world when you looked at that and went, giraffe, standing upright in a far setting, right? Basically, these pretext tasks force the system to learn a tremendous amount of knowledge about the world, whatever the world of your data is, that then makes it easy to solve a variety of other kinds of tasks with your data. And then now the final case, right? So the final case is case three, there's no labeled data. And, when does that happen? I just said because I don't have to anymore, right? So 15, 20 years ago, to think about actually learning stuff when there was sort of no data to learn from seemed ridiculous. But these days, it's not ridiculous. It's actually pretty common. So this is called zero-shot learning, right? One-shot learning would be, here's one X and a Y, right? Here's one X-ray, and here's a label as to whether it's a tumor or not. Zero-shot learning says, I'm not going to give you any examples. And so the way to handle zero-shot learning, as I said, there is no free lunch. These machine learning systems can't make things up out of thin air. What companies like OpenAI have done is to essentially gather very large volumes of data, which are text and images. So, you can go out to any social media site, find tons of pictures of things. You post a picture from your vacation and you say the family playing bocce on the beach. So now you got a picture of a bunch of people. They're out in a beach scene and they're, throwing bocce balls around. So what the companies have done or what these approaches do is they leverage that. And remember I said that the idea is that all we care about in machine learning these days on some very abstract level, which is kind of real, is to take a thing and turn it into a vector of numbers. So we can take a sentence like mountain landscape and turn it into a list of numbers, 1.29, 0.76. We can take images and we can turn those into lists of numbers. And so what these systems do is they essentially have ways of encoding text into lists of numbers, ways of encoding images into lists of numbers. The magic happens where they force those encodings to be the same or to be similar for images and their associated captions, right? So if you look that I've got this mountain scene here, a mountain scene here. This is 1.29, 0.76. That's 1.21, 0.81, right? It's like pretty similar. So the idea with this zero-shot image classification is that you've got a system that already knows how to turn pictures into lists of numbers and text into lists of numbers. And then if you want to find something weird, like you say a widget is an upside down bar stool with a laptop sitting on it. What that does is it will take that sentence and it will turn it into a list of numbers. And then you can look at that and say, well, what images look very similar to that thing? So now what you've got is you've got a representation of an upside down bar stool with a laptop on it that you can then compare to images. And if you find images that are similar to that text encoding, then hopefully you found an image of the thing that you're looking for. And then the last example I want to talk about, and this one is kind of crazy to me. So you can do zero-shot document classification, and we have a project where we're doing that right now at Synaptic. So quite a few years ago, we did some work with a legal firm in the immigration space, and they wanted to do document classification. So it turns out that if you're immigrating to the US and you're trying to get a visa, they ask, as you would imagine, for lots of different kinds of documents. There's passports and driver's licenses and government forms and transcripts and resumes and things like that, right? The old school way of solving that problem was to extract visual content from the document, use terrible OCR that was available at the time to try and extract text from it, and then just train up a classifier on it, right? So what you had to have was a bunch of documents, and humans had to go in and say, that's a transcript, that's this government form, that's a passport, right? Now, it turns out that you can do that zero shot these days with large language models like ChatGPT. And so you go, hey, there's an invoice contract that has an invoice number, an invoice date, and a total amount, right? So it's almost like a little database schema. A driver's license has a name, an age, and a license number, right? And I go, oh, well, like the age is an integer and these things are strings. So all I'm doing is I'm saying, hey, language model, here's stuff that's inside of an invoice. Here's stuff that's inside of a driver's license. And then I go to the language model, I go, hey, here's the text I scraped out of that document. And then here's the stuff I expect to see in those different types of documents. Fill it out for me. Figure out what document it is and then extract the information. And it'll go, boom, here you go, right? Like, this is an invoice, and I think it's an invoice, and I'm going to also tell you what I think the invoice number, date, and amount are. So it's zero shot in the sense that all I'm doing is I'm saying, here's the fields that are in the document. I'm not even going to show you any documents in the training phase. So why is this not a free lunch? It's not a free lunch because OpenAI has spent tens of billions of dollars in sort of training these models, right? So that thing knows so much that you're able to just give it a little bit of information about the thing that you're looking for, and it'll go, yeah, okay, I can solve that problem for you, right? Similar kind of thing here with image classification. Their original model, this thing called CLIP, which was contrastive language image pre-training, they had 400 million caption pairs, right? So they had jammed an enormous amount of knowledge about the relationship between text and visual appearance into these models. And all you're doing is you're using that as this sort of, I've got a lot of prior knowledge, right? I know a lot. My model knows a whole lot about how text and images relate to one another. This model knows a whole lot about almost everything in the world. And I'm just going to provide you a little bit of information. I'm not ever going to train a model, and these things will go off and just rip through documents and be, like it's a little bit of an art to making it work well. But it's one of these 80-20 things, right? The simple sort of dumb first thing that you do gets you 80% of the way there. You got to kind of fight to get the last 20%, but you can get there. Okay, so just a few concluding thoughts. One slide, and then we'll be good to go. What I wanted to do today was to kind of give you an intuition about when you need more or less data. Also to like expose you to some of the general strategies that are used in when you don't have a lot of data. But then also, I think importantly, to convey the idea that you don't have to have your data house in complete order. So I've had lots of conversations with potential clients, and they're like, yeah, like we really want to do AI, but we got a year and a half of building a data warehouse ahead of us, right? And so, that's great. It's important, especially if you feel like your data is critical to the value that you're offering or will be offering. You need to get your data in order. But it's also the case, and I'm hoping I drove that home a little bit today, that you can do a lot. You can solve point problems, even if you don't think you've got a lot of data. So remember, more data is almost always better. But the less data you have, the more experienced your consultant needs to be, or your data scientist on staff needs to be. So it makes it harder. It's not impossible, but you have to have a bit of a broader view about how to solve these problems. So remember, if you don't have much data, you can use somebody else's model. You can do transfer learning. You can use somebody else's data. You can scrape it from the web. You can look for online data resources, or you can just make more data through data augmentation. I will say that data augmentation, there are a ton of strategies out there, and I touched on a couple of the most simple ones. If you don't have much labeled data, then you can leverage either certainty or uncertainty in your model, right? If you're leveraging uncertainty, you're doing active learning because you're getting a human to help you out in regions where the model doesn't really know what it's doing. If you're leveraging certainty, then you're doing self-training where the model is like pretty confident. So yeah, I'm going to call that thing, it's a tumor because I feel pretty good about that. Or you can just learn your own representations without labels, right? That was the giraffe that we were masking and filling in. And if you've got no data, there are zero-shot learning methods. So, if you want to learn more, you can Google zero-shot learning and you'll find all kinds of resources around that. Okay, so I'm going to pause for a minute and let Sam say a couple of words, and then we'll see if there are any questions.
Great. Thanks, Tim, for a great presentation. We are taking questions, so if you do have any, please submit them either in the chat or in the Q&A section. Tim will be glad to get to those. And while we're waiting for any of those questions to come in, I want to invite you all to our webinar next month, Tuesday, September 30th, at the same time with our same speaker, Dr. Tim Oates. I'm going to add the registration link to the Zoom webinar chat. And this session is titled Guardrails for LLMs, Keeping AI on Track. In this session, we will explore practical strategies for ensuring your large language models stay on track, answering questions the way that you intend. And again, I'm going to be adding that to the chat here, so you can go ahead and register. We will be recording that session as well, so if you're not sure if you can make it, register anyway so you can get the recording. And I haven't seen any questions come in yet, so we'll wait another minute or two. But thank you again for joining us. Tim, if you have any concluding thoughts, I'll let you say that before we end the session.
Okay. Yep. No, that's good. I'll just hang out and see if there are questions.
Okay. It doesn't look like we've had any come in so far, so we'll go ahead and end it here. Hope
Okay.
everybody enjoys your day and be on the lookout for it via email for those recording and session slides. Bye, everyone.